very happy to be here, to be sharing my work with all of you, and thanks for the food and for the warm hosting here. So again, yeah, thanks for the Yale Himalaya Initiative as well for making this happen. So basically, in the next 45 minutes or so, I'd like to share basically work that I've been doing for the last almost 10 years now. Basically since the start of my PhD. So instead of just focusing on one paper, I'm sort of giving an overview of all of the work that I've been doing. I think that sort of encapsulates all of my work that I've done in this paper. So yeah, as Vartendra pointed out, I'm a geographer, but I'm trained as an Earth system scientist, so I do rely on a lot of modeling, remote sensing, field-based observations, so mostly from an Earth science perspective. So yeah, we've certainly reached a lot of global milestones over the last, particularly in the last 5 years, and I'm sure most of you are familiar with this. We've certainly exceeded the 400 parts per million global carbon dioxide concentration, as you are familiar. I teach at a business school, and coming from earth science background, it's certainly a very interesting setting. And what I tell my introductory, earth science, physical geography students is that this is probably the most important graphic from this entire class. It kind of shows the extremity of the problem that we are arriving in right now. Because carbon dioxide certainly has exceeded this 400 parts per million, certainly in the last million years, but probably also in the last several million years. And we certainly see, year after year, the records being broken, global average temperature records being broken year after year, particularly again in the last 10, 15 years. And we see the global changes, large-scale changes happening, right? So this is the Arctic sea ice extent. The blue line indicates the 2018 extent in millions of square kilometers. So well below average, the normal average Arctic sea ice extent. We also see, increases in sea level rise. So there's again plenty of evidence of these large-scale global changes. At the same time, humans have also changed the landscape completely, right? So this top panel shows the natural vegetation that would occur if humans were absent from the planet. So before we started, farming and agriculture, this is the natural vegetation that would occur. So this is the type of sort of map that would, we use regularly in global climate models to, run this natural vegetation scenario. This middle panel here shows the amount of croplands, right? The impact of agriculture. So all these red pixels here, they're covering an area of about 16 million square kilometers, so roughly put together the entire continent of South America. The last panel here shows pasture and rangelands. So this again put together is roughly the size of the continent of Africa, so 30 million square kilometers. So between climate changes and the impacts of anthropogenic changes, we certainly are bound to have changes in not just the hydrological cycle, but also other elements. So certainly I'm interested in the hydrological cycle, how both climate and anthropogenic changes impact various processes, particularly in the high mountain Asia is the work that I'm presenting here today. But I also work in the Amazon River as well, which is a completely different environmental setting. And we have seen evidences of changes in hydrology, right? So this first panel shows the changes in precipitation trends from GPCC data here. So the red areas indicating decreases in precipitation trends, millimeters per year, decade. So the darker color you go, the drier the places are, or the rainfall is getting less. The blue areas are indicating wetter areas, getting more precipitation. The lower panel shows, again, changes for stream flow, trends in stream flow for some of the large river basins. Again, same scenario, but it correlates very well with the precipitation trends. Red indicating decreases in discharge. So these areas are decreasing in discharge. The green is indicating increases in discharge trends. So again, we see these changes happening particularly over the last 50, 60 years, since 1950, where the data shows. And we know that the global climate projections indicate also, wetter places getting wetter, drier places getting drier. Right? So that's the story we usually hear from climate projections, and this is the projected change in hydrology and stream flow for an average temperature increase, global temperature increase of 2 degrees Celsius up until 2050. So red areas indicating percent change, negative changes, blue indicating increases in precipitation, stream flow changes. So again, wetter places getting wetter, some dry places getting drier here. Now, mountain regions are certainly one of the most fragile and vulnerable regions, it occupies about 1/4 of the land surface, about a quarter of population living within the mountainous regions here. And because of the steep gradients in elevation, topography, climate, vegetation, and hydrology, makes this a very challenging area to work in, particularly with regards to climate processes, but also projection of climate signals. So I'm sure all of the people in the audience here today, if not most of you, are familiar with this region. So I probably don't have to go too much into detail explaining where this is. So this is the Hindu-Kush Himalayan region that I'll be talking about in my work today. Again, the region spreads from Afghanistan all the way to Pakistan here in the east. We got a predominantly monsoon season affecting the eastern central Himalaya. Sometimes going as far as the Karakoram here, right? And we certainly have some of the largest river basins, the Ganges, Brahmaputra, Mekong, Yellow. About 1 billion population in the greater Himalayan region being supported with these water resources. So certainly a very important resource in terms of potential climatic changes. And we do know that this valuable resource is under increasing threat with increasing temperature increases. So we have recent research. This is a paper from Gautam. Ritesh Gautam shows warming at the rate of 3 times the global average occurring in the Himalayan region. And we do know also that the glaciers are also losing mass here. This is the cumulative mass balance. The Himalayan region here is in this black line here. So we're right on the average compared to all of the global regions. So to give you an idea of how much mass is being lost, between 2003 and 2009, this region, high mountain Asia, lost about 174 gigatons of ice, which is about 9,000 sports stadium filled with ice losing annually. So just to give you something that you can compare with. So we're losing a lot of ice here. And within the greater Himalayan region, there are certainly various processes, just because, as I mentioned, there are steep gradients of elevation. Even though monsoonal precipitation dominates much of the rainfall and the hydrology here, as you go further up, we see more snow and glacial melt dominating the hydrological processes. So this is a conceptual diagram. I just threw it back down. The background is actually Langtang village in Nepal, but it kind of shows some of the basic processes that's occurring here. My work mostly tries to understand a lot of these processes in these high mountain areas. I'm trying to understand snowmelt processes, the snowmelt hydrology. So I'll be talking about some of these processes, what are the challenges, what are the opportunities, what are the successes. So I'll spend the next half an hour on this. So this is the research overview today, if I were to summarize it. First I'll talk about characterizing these snowmelt processes. How can we, in such a data sparse region, how can we get a good sense of some of these processes that are occurring in this large region? Snowmelt processes. I'll also touch on permafrost a little bit. And I'll talk about challenges and opportunities in hydrological modeling in this region, especially when we have very limited data. It's a big challenge, as most of you are familiar with, those who work in this region. Not just the environmental data, but also socioeconomic data, everything. It's a big challenge here. And finally, talk about climate extremes and hazards in the region. What are some of the hazards? What are some of the extremes going forward? So again, as an approach, as an Earth system scientist, I usually rely on various types of data sets. I simulate data sets. I use modeling. I scale up using remote sensing, but also based on field observations. And that way I can sort of get an overview, larger picture on any processes that may be occurring. Right, so the first ever paper that I actually worked on was, I was interested in snowmelt process. Can we somehow characterize what's happening in terms of snowmelt. Simple thing like when is snow melting, when is things freezing up in the Himalayan region. So I was very interested in this basic process. And again, I want to know the entire region, right? So I'm interested in the entire Himalayan region. So for this, I used a data called QuickStat data. It's a radar data, active microwave from NASA. The data is available from 2000 to 2009. After that, the mission actually collapsed, so we only have 9 years of data, but very rich data. What this allows us is, it allows us to look at this entire region at almost near daily temperature resolution, 2 to 3 days apart. And we can also look through day and night conditions, and it's not affected by clouds, so we can benefit from clouds. And the other good thing about this active microwave data is, as soon as it senses water in the landscape, the signal drastically changes. So here what I'm doing is I'm showing you data from 5 stations, 3 from Everest region, 2 from Western Himalaya. This black line is the signal from the satellite for the 9 years period. The blue line is the temperature data from that particular pixel here. So what you see here is, as soon as temperature goes above 0 degrees Celsius, which is, as soon as things start to melt, the water appears on the landscape and you see this decline in the signal. So this is fairly consistent through all the stations that I examined in these high mountain stations. So basically what I did was I used this data, extrapolated to the entire region. So I can now get the snowmelt maps for each year for the 9 years, right? So each year I can, with some accuracy, I can say when things are melting up, when things are freezing up. So this is the melt onset. When does melt occur across the Himalayan and Karakoram? So here I'm only focusing on the Himalayan and Karakoram regions. So if I were to average this out, this is what it would look like. These are the dates of melt onset in this region. So typically melt onset is occurring earlier in the eastern central Himalaya, but it progresses as you go further west. Again, there's a separation with elevation, right? So lower elevations will melt earlier, higher elevations again melt much later. So there's that topographic variability also embedded within this regional variability. Same thing, we can also now find out when things are freezing up. And again, we get the same data for each year. I'll show you the average here. So average freeze up dates. When things start freezing up, so the higher altitude areas start freezing up earlier. You also see that the Western Himalaya here has an earlier freeze up, but as you go further east, things are freezing up a bit later on average. But again, there's elevational variability here as well. And if you take a difference of the freeze up and the melt onset, then you get the melt duration. So on average, the Eastern Himalaya up to central Nepal here has a longer melt season in terms of number of days in a year. As you go further west, you can see there's again differences because of topographic variability, but on average, you see that Eastern Himalaya has a much longer melt duration. So again, you can look at various statistics with that data. I would say that the only significant difference that usually we see is that Eastern Himalaya on average melts much earlier than the rest of the region here. It also freezes up much later, which ends up being that the Eastern Himalaya has a significantly longer melt period overall compared to central Karakoram and others. So again, there are elevational statistics that I could as well show, which basically will say that the lower elevations on average melt about a month earlier than every 1,000 meters you move higher up. Again, this data we can also examine at various. This is a data that I prepared for a CGIR group, again for focusing on Western Himalaya. So we could, again, this data obviously, the more ground data we have, the better validation we can do for a lot of these data sets. So potentially with modest data or upcoming data, we can make sort of this data set even much further richer. So in summary, this was the first paper that kind of mapped snow melting processes for this entire region, for the entire Himalayan region at least. And again, there are fairly conclusions that I already mentioned earlier. Areas that have a longer melt season also tend to melt earlier and also tend to freeze later, typically in the Eastern Himalaya. Right, so another process with regards to the cryosphere is permafrost, which I believe is almost one of the areas that we don't really hear much about at all for the Himalayan region. We hear about permafrost in the Arctic, which is thawing, causing a lot of issues with regards to releasing old carbon that has been locked up in permafrost. But very few studies have tackled permafrost in the Himalayan region. Why? Just because we don't have any data here. We don't really have a lot of data at all. But we do know that there's potential impacts when permafrost thaws, right? So what is permafrost? It's basically anything soil or rock or ground that's been frozen for at least 2 consecutive years, below 0 degrees Celsius. So these are some of the, basically you see the cross section, you'll see these ice blocks on the rocks and soil. And we do know that this exists in the Himalayan region. It's not that we haven't really had any significant data being collected. The only data that's coming about permafrost is from the Qinghai Tibetan Engineering Corridor, mostly because there's a lot of big projects, pipelines and everything that's being planned in this region, so there's a lot of data coming from that particular region. It's sort of this narrow belt region. But most of the Himalaya, we have very few data. So in a paper led by Stephen Gruber, he used this global model based on elevation, solar radiation, mean average annual temperature. We basically try to infer where is permafrost existing, what might be the distribution of permafrost, this frozen landscape in the Himalayan region. So this kind of shows the modeled distribution and zonation of permafrost. So as you can see, the Tibetan plateau certainly has a high probability occurrence of permafrost. And as you go sort of these areas, that's only in favorable conditions, right? So you need to have the main criteria is you need to have ground that's 0 degrees Celsius for 2 consecutive years at least. So there's potential melt impacts from these melting of the permafrost. And it could be geological hazards, it could be flooding, it could be ground subsidence, it could also have groundwater hydrology impacts, and it could also have vegetation influences. So again, in this paper we only kind of scratch the surface with this modeled output. Some progress has been made. ICIMOD in Nepal has installed 25 ground temperature loggers in the Langtan region. So again, this is a very initial startup right now. We would probably need extensive coverage of these ground temperature loggers all through the region to get a better sense of what's happening to this frozen ground up in this region. So my second topic is snowmelt hydrology. My basic question was, how can you characterize uncertainties associated with snowmelt hydrology? Whenever we model hydrology, it's basically an understanding. We're trying to understand how the processes work with any model. And with any model, if you're a model, you know that there's various parameters that you have to tune in. And typically, when you have a model, you want the parameters to be tuned from ground observation or field observations. And then we can sort of have a better idea of what the value might be. And we know Himalayan is very data sparse. So a lot of the models, and a lot of the times, we're basically coming up with these approximate ranges or values from other studies. And we're trying to see how can we get the best fit in hydrology. So there's a lot of uncertainty involved in this. So I was trying to, certainly one of the most challenging papers I worked in terms of quantifying errors. Over the last 10 years, we do have actually a much better understanding now in terms of snowmelt contribution in the Himalayan region. A lot of the work has been pushed by ICIMOD along with Future Water in Netherlands and various other teams, and we know that there's certainly a monsoonal precipitation. As a result, there's a big contribution of monsoonal rainfall in this region here, but as we go westward, that influence decreases. So we start to see more snow and glacial melt contributions in the western Himalayan or the Indus Basin. So we have a fairly good grasp of this general overview, but it's the details, like the processes that we are trying to understand even further as you go in a particular region. So again, this shows the same graphic here. We are showing here different components. So the glacial, the snowmelt, the blue indicates rainfall, and the base flow. So again, as you can see, the eastern and the central Himalaya, we have a big percent, 70% on average of rainfall contribution from the monsoon. If you go to the Indus Basin, we see a bigger snowmelt and glacial contribution here on the annual runoff balance for these big basins. And we do know the glaciers are changing, right? So glaciers have been retreating for a long time here in the Himalayan region. This map here shows the reduction in the thickness of the glaciers from observation. So all these red areas indicate about this would be 10 meters thickness reduction on a glacier at each of these locations. We do know that there's a few glacial shortages happening in the Karakoram, but overall we see reduction in glacier thickness and also retreating glaciers. So this is going to impact the contributions from glacial and snowmelt as well in the hydrology. So there's a lot of challenges. There's a regional heterogeneity, there's topographic variability. We don't have a lot of data above 4,000 meters. So how do we don't have a lot of precipitation data. We are using gridded rainfall data in some cases. We're using very sparse observations of rainfall data to model the hydrology of this region. In my study, in this paper, I basically chose this particular basin in the eastern Himalayas, the Tamar River Basin. And I used a simple snowmelt runoff model based on temperature. I'm not going to go into the details of this model, but and again, as I said, we have a number of parameters in this model. And if you're a modeler, you know you have to tweak these parameters if you really don't know what the value is. What I did in this was I basically combined this Bayesian framework that basically allows us to give a range if you don't know the exact value. And hopefully, as the model sort of equilibrates, you have a fairly good understanding of what the value might be. And what this allows us to is to look at the uncertainty with this parameter. So that was the main question that I was addressing here. So what I found out was, yes, in some of the very sensitive parameters, the process actually helps us to narrow our range. So something like a lapse rate or critical temperature above which the melt happens. So the Bayesian model allows us to sort of come up with this unimodal distribution, which means that the model was able to find an average sort of value for that particular parameter, right? So again, ideally we want to measure these temperatures on the field or with actual data, and we want to put that value in the model. And with lack of data, we are sort of basically left with these sort of frameworks. So the good news is that the model does fit the hydrology shape very well, and it does allow us to constrain some of the most sensitive parameters. But what I also found out was that just the uncertainty in the parameters does not account for the overall uncertainty. So here I'm looking at the uncertainty bounds, and it's not able to capture all of the uncertainties here. Why? Because our input data is not able to capture that. So our model is only as good as the input data. So the main driver here in South Asia is precipitation rainfall. So unless we either correct the precipitation data, or we somehow have a good way of lapsing the rainfall data into higher altitudes, we'll always be left with this sort of uncertainty driven by input precipitation data. So again, input data plays an important role when you're doing anything with hydrology in this region. So recently I was getting into this idea of, I was asked to write a book chapter on climatic hazards in this region. And this is what got me thinking, what is a climatic hazard? And are there any extremes or hazards in this region? And again, I like to quote Catherine Hill whenever we talk about, she's a famous climatologist, and she says that hazard or a climate hazard is not going to be something very biblical or something new. It's just going to be something that's already happening, but it's going to happen probably more frequently. 9 out of 10 times, it's probably going to be the same extreme weather or climate event, just more frequent. So again, it's likely it's very reasonable that with the increasing climate change and temperature increases and uncertainty with precipitation, there's a good connection between climate change and these hazards in this region. And again, we don't have a full grasp of this for this region yet. So basically, in this paper, we basically provided a summary of some of the major hydrological hazards. What are the trends? What do we know about the state of these hazards in the Himalayan region? So again, I'm listing some of the major hazards, so hydrological hazards, extreme events from climate. I mentioned some of the atmospheric hazards, and also the regional or the overall regional sort of vulnerability to food security resulting from this. So this is the emergency database, which is basically a catalog of all of the hydrometeorological disasters that have occurred globally, particularly in the South Asia region. So I basically compiled all of the reported events from 1950 up until present. So these would include flooding, landslides, all of the hydrological and meteorological events. So we certainly see a positive trend as we come closer to the last 10, 15 years. Certainly there's a bias in reporting. Like we are reporting more events as we come closer, we're recording more. So the bias has to be obviously kept in mind. But nonetheless, this is the trend that the database shows based on what was reported, what was recorded in terms of all of the events that have happened. Flooding is certainly the most common hydrological hazard we see in this region. Very common, as you all know, with the monsoonal flooding, monsoonal precipitation that happens between June and August. Eastern Himalaya is more vulnerable to this sort of flooding every monsoonal season, but sometimes, as you know, that it sometimes goes all the way. Flooding can occur even in the Western Himalaya. I'm sure Vartendra is very familiar with this flooding that happened in the Uttarakhand region. 360 millimeters of rainfall in a few days that caused this immense flooding there back in 2013. 2017 was a big flooding year last year. Never made the news except for BuzzFeed, I think, because it was dominated by the Houston flooding that happened at the same time. But I mean, there was massive catastrophic flooding all over the lower plains in Nepal, in India and Bangladesh. I think this number is actually higher now. Huge population impacted and displaced, same with children. If you look at the accumulated precipitation of rainfall for that 7-day period when this rainfall occurred, it's actually some places received almost 1,000 millimeters of rainfall in a few days. And I know Houston took a lot of the news, but we're seeing almost the same rainfall, if not higher amounts, but just a massive region here, right? So again, I just wanted to highlight the intensity of this event that occurred in last August. And again, I'm showing a few districts in Nepal that were severely affected. This is compiled by EC mode primarily, but using radar data shows the extent of flooding, and it captures the water very nicely here. This is the Saptari district. You can see Moram district also affected extensively, displacing a lot of people here. And overall, if you look at the entire sort of South Asian region here, you can see this is a very expansive sort of region that was affected. And the number of people dead, number of people displaced, again, a huge population that was affected with this. So again, I know that in the US, anytime there's a big hurricane that comes through, there's this debate of, is it climate related or is it just a one-off event? So there's a lot of climate attribution studies that's happening now in I would say in the West, where we're trying to sort of put a probability or put a chance of, is this because of climate change, or is this somehow enhanced because of climate change? And in a lot of cases, the answer is yes in the US. And we still, I think, we still have some of that studies, I think, can still do in this region. I mean, August 27th flood, how much was because of climate change, or how much is this just an extreme event that just appeared, just once? So again, these attribution studies I haven't seen for the Himalayan region yet for some of these events. I think there's one paper that talks about the Uttarakhand flooding a little bit, but not so much in detail yet. I compiled the monsoon event data for Nepal from the Department of Hydrology and Meteorology. So when does monsoon arrive, when does monsoon leave? This is from 1968. So this is the record kept by the DHM in Nepal. So again, not much of a trend in the onset of monsoon, but this is the trend of when monsoon leaves basically Nepal. So certainly a slightly positive trend. I haven't really done any significant testing or anything, but if it's leaving a couple of days, if it's sticking, if monsoon is sticking for at least 7-10 days late into October, we certainly have an extended monsoon season, and that could potentially lead into potentially more flooding and landslides. So certainly climate change is supposed to, without climate projections, we can see what the future might hold in terms of climate extremes. This was a paper that I basically analyzed all the climate projections, all the climate extreme database that we have from the various IPCC records, so the IPCC4, the IPCC third report. Basically shows that, again, the extreme temperature range, I'm just showing two indicators here, the intense precipitation range and then the extreme temperature range. So again, for both eastern and western Himalaya, we see this sort of, obviously a very negative picture as we go towards the middle and the end of the century. Again, this is showing the same. What we see in particular that's alarming is for the eastern Himalaya, we see that there's significant shifts in these climate extremes. So what I'm showing here is climate extreme. So if you just want to focus on the frost days and warm nights. So this here is our distribution for the last 30 years for the number of the density of frost days. What we see as we go into middle of the century and then the end of the century is that we see these extreme days, frost days declining, so shifting this entire distribution. Same with warm nights. So the nights are getting warmer significantly, so we see the complete distribution shifting. I would say some of these are alarming for the eastern Himalaya region in terms of climate extreme. But this sort of trend is kind of consistent across the entire Himalayan and Hindu-Kush Himalayan region. Right, so I think we all hear about the outburst first, the glacial lake outburst floods, also known as GLOS. Usually these are moraine dammed lakes that basically drain all of a sudden because of moraine failure. This is a picture taken by Uliana Hordowski in Science in the Wild at UC Boulder. It shows how much water can be sort of discharged in a 24-hour period. Yeah, it is alarming because downstream villages and communities can be swept away or destroyed, and it has happened in the past, right? So we know that in Nepal alone we have recorded 14 of these outburst flood events that have happened. So, assuming that the climate increases, the climate continues to warm, one would expect this to potentially carry more risk. And we do know that there's ECMOD has mapped all of these lakes all across the Himalayan region, and we know for each country how many lakes are potentially dangerous going forward. The next slide is actually a very interesting slide that kind of sums up what science is. Every day science is adding new data, new studies is coming out. So this morning I woke up and I checked my Twitter feed, and there was this new study that came out for glacial lake outburst flood. And I said to myself, I have to show this if I'm showing this image here. So what did the study that came out today say? It was by Harrison et al. In the journal of the open source journal in Cryospheric. So it basically shows, if you just focus on the blue lines, these are the number of cumulative sum of these outburst flood events that have happened globally. So what this shows is these flood events peaked globally started from the 1940s, peaked around the 70s, and since 70s actually the flood events have been declining. As you can see, the flood events cumulative sum has been declining here. So the peak was around the 1930s. So what they attributed to this peaking was actually that we know that the deglaciation has been occurring in the Himalayan region since the Little Ice Age period, and particularly since the early 1900s, things have been melting, glaciers have been retreating. So they're basically saying this was a response to that melting and retreating that has been occurring, and this was a lagged response of that melting that has been ongoing. If you focus on the Hindu-Kush Himalayan and the Pamir and Thienshan, we see the same sort of peaking of these cumulative events in the 70s. So there was a lot of events happening around the 70s, and since then it has sort of slowed down. The Alps, the European Alps also saw this same trend. And we would have more confidence because we know that in the Alps they have a much more longer data set about these events. So if they are showing a similar distribution, the authors basically said that we have more confidence in these sort of trends. What they do say is that the warming that we have been seeing in the last now 30, 40 years, this intense warming, this is probably going to have a lagged response in the coming 20, 30 years. So we might see potentially a surge in these events from this intense warming that we're seeing in the last 40 years. So it's going to have a sort of a lagged response, potentially going into the middle of the century. Now, again, with monsoon, we also have landslides. It's triggered by the rainfall. We have seen an upward tick in the number of fatalities in Nepal alone, keeping a record of how many people have died with landslides. This is an image of a Sunkosi landslide in 2014. 156 people died, and this is an image from Landsat. Again, there was a lake that formed upstream of this river, and we had to drain this. So again, these are some of the hazards that are sort of fairly common. This is the trend. This is a blog that Dave Petley, he's sort of the landslide guru. He keeps a record of sort of the global landslide inventory. This basically shows the number of deaths in the dotted line. The solid line is the number of landslides. So this is for Nepal. Again, there's a lot of variability, obviously, but again, there's a slightly upward trend, I would say, if I had to draw a trend line here. 2016 was the worst year since he started keeping record from 1980 in number of landslides here. I was actually in Nepal in 2016, and I remember seeing all these news clips and media all over when I was in Kathmandu. Traveling was almost impossible with landslides and basically all throughout the country. So again, sort of a visual confirmation that 2016 was the worst in terms of total number of landslides that occurred in Nepal. Again, this is not my expertise. My colleague Ritesh Gautam is the main sort of expert in atmospheric hazards, but he's documented that there's also increasing atmospheric hazards when you talk about South Asian region here, Himalayan region, particularly in the Indo-Gangetic plain. So this map here shows basically the fog or low cloud occurrences. So basically, there's this phenomenon called ABC, or atmospheric brown clouds. That basically is like this sort of thick smog that traps air pollutants, causes fog and haze, air visibility, transportation issues. And if it lingers for a long time, if the number of days is sticking around is long, it could potentially have negative health impacts, airplane sort of chaos, and also visibility issues. So he's documented that this has been more increasing in terms of number of days, more recently, particularly right along this Indo-Gangetic plains. So again, with water, I think we're all kind of interested in this overall vulnerability of this region, right? So particularly with water, we know that 90% of a lot of the water is going into irrigation in these respective countries here. Agriculture is the main sort of in this sector that's using a lot of this water here. So food security becomes an issue as you're going forward, projecting water availability in this greater Himalayan region. Again, this is sort of this flow diagram that shows from Ellie Biggs. Same statistic, 90% of water withdrawals going to agriculture. Again, we have food production issues for this region. And again, water is the central theme here. So if precipitation is changing because of climate change, how does that sort of effects are cascading downstream all the way down to food security, food availability, all those water security rates, so all of these things. Again, this is sort of the trajectory, I would say. I see my own research sort of heading towards from this sort of Earth system science perspective. For instance, energy security. So Nepal, again, we have a promised capacity of very high megawatts of electricity, but we're only generating about 600 megawatts of electricity. So again, hydropower becomes another issue within this security. And with hydropower and dams, again, we cannot neglect the transboundary water issues in the Himalayas. This picture here from this science paper shows a lot of the proposed dam sites along the Himalayan region here. Again, there's a lot of these proposed dams. There's a lot of inter-water boundary diversion projects that are sort of thought about. And if all of these were to realize, it actually is very detrimental to the Himalayan diversity, biodiversity, the environment there. I saw a report coming out from Norway that said that 80% of endemic species in this region are already a threat or going extinct. So again, these hydropower sort of projects again still have to be realized as of today. So in one of our recent papers, which is still in review, we started looking at what could be the impacts of reducing water availability or glacial melt or snow melt to hydropower. Typically we focus on run-of-river hydropower, which is more common in our country, in Nepal, and also several other countries. In this paper, we actually compared across these Nepalese watersheds and also looked at a few other watersheds in British Columbia and Washington State. So we again use simple calculations to compute glacial runoff. We looked at detailed mass balance studies coming out, glacial mass balance studies, so from each of these watersheds. And if you know how much the glaciers are melting, if you know the glacial area, we can roughly calculate how much is contributed by glacial runoff. So roughly, we can come up with a glacial contribution to these basins. These numbers are in good agreement with several other studies that have been published recently, again from ICIMO and from Future Water. Again, what we find is that in terms of the British Columbia, actually, we see much more negative changes in terms of reduction of glacial contribution going into the future. In Nepal, we see that, and in British Columbia, we see that usually the smaller basins with smaller glacial coverage is actually, those are the ones that are harmed the most in terms of glacial contribution. So in this case here, we see Sunkoshi River Basin watershed having a negative change in percent glacial contribution, but we see in Kali Gandaki and Marshangi, it's actually a positive, or if not, it remains the same. Why is that? It's also because in this region we are reducing the glacial contribution, but we're increasing the pre-monsoonal and monsoonal rainfall amounts as you go into the future. So we're supposed to get more weather as we move into the mid-20th century. So again, this is again to highlight the temperature changes, the precipitation changes, how that is connected to the regional hydroclimate through agricultural production, extreme climate events, snowmelt, glacial hydrology, also changes in natural vegetation, which I haven't really touched on today. But we all know that vulnerability of this region is a very complex picture, right? So I'm only touching on the climatic and environmental factors, and I know that most of you are working in very important fields, socioeconomic, political economy. Again, hazards, this is a very climatic perspective of natural hazards. And we know all of these conditions actually create the overall vulnerability of this region. So we need to look at all of these components as well, right? So are certain populations vulnerable to a particular hazard versus another population living in the same region? So again, it's not an easy story, which is why I think there's a lot of people working with socioeconomic data with hazards, even when I talk this afternoon. So now, what are some of the work that I'm interested in? For my postdoc, I actually worked in the Amazon for 3 years, where I was looking at the impacts of climate and impacts of deforestation. So the Amazon is heavily deforested. So what I was trying to do there is, if I know the hydrology is changing, what is caused by climate, what is caused by humans in terms of land use change. So I wanted to try, going into that direction. Can we do the same for the South Asian basin summit? What is caused by, if you have a hydrological data set for the last 50, 60 years, how has the hydrology changed because of climate versus how has it changed because of human anthropogenic land cover changes, such as deforestation, urbanization? Another aspect that I'm working on currently is mapping glacier velocity. I'm interested in mapping velocities of glaciers. How do they differ? Because we have a big region in the Himalayan region, right? So, if a glacier is ending on a lake versus if a glacier is not ending on a lake, do the glacier velocities differ? There was a recent NASA project that basically it's a group of projects, about 10, 15 projects, that came up with this really rich elevation data set for the Himalayan region from 1950s to a current period. They basically compiled every single image that is available and they came up with this rich elevation data set. So I think with that data set we can, this is velocity data for the Kumbh region that we produced as a part of a workshop, but this kind of shows the ability of mapping velocities of these glaciers that are flowing here. So my other question is, can we map glacier velocities across, let's say the last 30 years? How has this changed over time as well? So I think that elevation data set might make some of these questions, feasible. And finally, I'm certainly interested in the human-environment interaction overall. That's sort of the ultimate goal. As I explained earlier, yes, the climate extremes and vulnerability is increasing, but how does that interplay with the social and economic data, the political economy of that region? And this sort of water, energy, food, climate nexus, where water resources is sort of this central theme surrounded by issues such as food security, energy security, water supply availability. I think this is the framework that we see a lot of sustainability studies. I think a lot of recent papers on sustainability and this nexus of these three. And we've seen several papers recently. So I think that's also a pretty neat framework to work on future issues in this region. So yeah, I think I basically threw as much that I had worked on. But again, there's a lot of collaborators and people that I have borrowed or worked with. Again, the last 10 years of